So let's continue to discuss some particular class of compact operators. So we defined compact operator. We started with finite rank operators, right? Let me recall. So this is finite rank operators. H is a Hilbert space. We always take a separable Hilbert space. Okay. Then this denotes all finite rank operators, operators whose range is finite. Okay. Then we define K of H to be the closure of this in the norm topology. Okay. There are other topologies which are not metrizable topology. There are other topologies called strong topology. There are many other topologies anyway. So this is the uniform topology, which is uniform convergence over bounded sets. Okay? It's equivalent to that. So it is with respect to this, we close it and it's a compact. When it is infinite dimensional, this is infinite dimensional. This is not equal to B of H. Okay. So then we prove spectral theorem for that T is in K of H. We prove T is in K of H is equivalent to saying there exists, it's diagonalizable, there exists an orthonormal basis such that TEN equal to, T is in that and normal. TEN equal to lambda n En and lambda n converges to 0. Okay. So this may be. I mean, in my screen, whatever I am writing, it is being blocked by the my image. But I want the video to be there. So I hope it's clear to you. Okay, it's visible to you. And it's visible in the video in YouTube also. If not, you have to tell me. Okay. So we proved this for any compact operator. So this is what is called compact operator. This is compact operator. Compact operators. Okay. Then we defined a trace for T in B of H. In T greater than or equal to 0, we defined trace of T equal to summation T for some En orthonormal basis. And we further proved that you can take any En, any orthonormal basis. It actually does not depend on basis. This summation does not depend on the orthonormal basis. You can take any orthonormal basis and do this. So this is what we proved last time. So this in particular, I mean, this does not depend on any orthonormal basis. Particular, it proves that norm T is less than or equal to trace of T. For, of course, we have only defined for T greater than or equal to 0. Okay. So this is because you take TXX. This is true. TXX is less than or equal to, this is positive, is less than or equal to summation T En is equal to trace T. By taking any O and B En with, we can start with one element and construct an orthonormal basis by Zorn's lemma. I think you must have seen this in when you constructed all these orthonormal bases and other things. You can actually, if you have some orthonormal set, then you can get an orthonormal basis. So one single element is an orthonormal set. Okay. So then you can construct an orthonormal basis. So if you have any orthonormal basis which contains this element, then this is true, of course. Okay, because all these elements are positive. Because T is positive means TXX is the inner product, TXX is positive. So all these things are positive. So this is true. Now we know that for T is positive means it's normal. Okay, T is normal. And we know we have proved that supremum of whatever we have in the left hand side is is the norm of normal operator. So this implies norm T is less than or equal to trace T. Okay. We have proved that since norm T equal to supremum for normal. For normal, and in particular, if it is a positive operator, it's a self-adjoint operator, so it's a normal operator. Okay. Normal means it commutes with this star, T star equal to T star T, and which is true for any self-adjoint operator. T is positive means it's self-adjoint operator. Okay. So because of this is true. Okay. So next, what do we want to do? Next, I want to prove that if you have a trace class operator, then it is compact. Okay. So proposition. So the TB in B of H, okay, then 1 if so, and I mean this is already defined, I believe. When you do polar decomposition, this is defined. This is T star T. T star T is a positive operator. Okay, T star T is a positive operator. T star T XX equal to TX, which is equal to norm TX square, which is greater than or equal to 0. Okay, so because of this, T star T is a positive operator, and Shruti in her class proved that any positive operator has a unique positive square root. Okay, I mean there may be lot of square root. There may be lot of, if you are given a positive operator, there may be lot of operators satisfying S square equal to T. But there is only one positive operator which satisfies S square equal to T, and that is a unique positive. So the positive square root is well defined, and that unique positive square root is what we have defined as we are writing it as half. So this mod T of an operator, is the positive square root of T star T. Okay. So if trace, so for any T, mod T is a positive operator. If trace of T is less than infinity, okay, then T is compact. That is one thing. Two, trace of T, I mean this is just mod T square. Trace of T star T is less than infinity, then also T is compact. Okay. This is what I want. So this is the proposition. So proof. So we want to prove that what we want to call, I mean, we will prove, so whichever satisfying this one, we call it a trace class operator. What all operators satisfying the second condition is what is called Hilbert Schmidt operator. We are proving that trace class, I mean, I haven't defined it. I will write the definition. So we are proving that trace class operators and Hilbert Schmidt operators are compact operators. So that's what we are proving. So for towards proving this, suppose I take an integer and then suppose trace of T power P. I mean, because I want to use P equal to 1 or 2. So I just take this trace of T power P is less than infinity. Okay. Then that just means mod T power P en summation is less than infinity. Okay, that's what it means. This means given epsilon greater than 0, there exists a n, okay, n a natural number, such that n equal to n to infinity mod Tp en this summation is less than epsilon. That's what it means by it is summable, right? Right. Now you take Pn from H to span of E1 up to En, okay, which is a finite rank projection. We take this projection on this. I mean, it's enough to write span because it's a finite dimensional space. So okay, you take the span of this E1 up to En, take this projection, which is a finite rank projection, which is in finite rank. Okay. So we want to prove that this Pn, so we have got a Pn, a finite rank projection. We want to prove that this Pnt converges to T in norm, right? That is what, these are all in finite rank. Okay, then we want to prove that P and T converges to T in this. I mean, I have assumed that trace of mod P power P is smaller than infinity. P can be equal to 1 or 2. Okay, so I will come to that. So we want this. We want to prove that P and T converges to T in norm. Okay, so towards that, let us take P and T minus T, or maybe T minus P and T, which is better to write. T minus P and T, norm of this, which is of course equal to 1 minus P and T. No, I want to prove that mod T converges. I want to prove this. From that, I want to conclude that T is also mod T is compact will imply T is also compact because of thanks to polar decomposition. We'll come to that. So T minus P and T equal to this. But here I cannot write. So I will better take mod T power P by 2. No, we are not proving this. Sorry. I'll write the following claim. I'm sorry. Claim is Pn mod T power P by 2. Okay, whatever P by 2 is. Converges to mod T P by 2. I think this will work in norm. Okay. So I have to write mod T power P by 2 minus Pn mod T power P by 2. Norm of this. This is exactly, this is equal to 1 minus Pn mod T power P by 2. Maybe I take the square. It's okay. So now this is equal to the C star identity. C star identity is this. T star T equal to norm T square. Okay. So I'm using that C star identity to get this is equal to 1 minus Pn. I mean, remember 1 minus Pn star equal to 1 minus Pn equal to 1 minus Pn square. So that doesn't matter. Mod T P 1 minus Pn. Okay. No. So check this. This is due to C star identity. Norm of T star T equal to norm T square. Okay, that's what I have used here. And of course, S T star is T star S star, and you are using all that. The elementary inequalities we proved for adjoints. So using that, this is less than or equal to trace of this. Okay, there is no norm. Because we have proved that norm is less than or equal to trace for a positive operator. So this is equal to summation. So this is 1 minus Pn. So this is summation. Wait, let me write the whole thing. N equal to 1 to infinity. 1 minus Pn. Maybe I'll take it that side. Okay, 1 minus Pn is self-adjoint. I can take it to the other side. Okay. Mod T power P 1 minus Pn En for some orthonormal. I mean the orthonormal basis which we have fixed there. En. Okay. Now this 1 minus Pn kills everything in Pn. Okay, it's an orthogonal complement of the subspace. It's a projection onto the orthogonal complement generated by the E1 up to En. So because of that, this summation is only up to n equal to n to infinity mod T power P En. And we have proved that that's less than epsilon. Okay. So we have started with this and we have proved this. So we have proved the claim. The claim is proved. Okay, so the claim says you hit mod T power P by 2 by a finite rank projection and it converges to T P by 2. So this implies mod T P by 2 is a compact operator. Okay. this implies there exists lambda n. This is a positive operator, which is normal operator. Okay, so there exists lambda n, which is normal. Okay, positive and normal. So this implies there exists lambda n complex numbers. I mean, they are all positive, of course. Because it's a positive operator, that has to be positive. With lambda n converging to 0 and en and maybe fn. We have used here some en, so fn orthonormal basis, such that Tn of fn equal to lambda, sorry, not Tn, mod t power p by 2 fn equal to lambda n fn. Okay. So if p equal to 1, okay, I mean, we have started with the p. If p equal to 1, this just says that norm t power 1 by 2 fn equal to lambda n fn. This implies mod t f fn equal to lambda n square fn. Okay. So this is also, I mean, mod t is also, this implies, I mean, mod lambda n converges to 0, I mean, lambda n square also converges to 0. So this implies mod t is in K of H. Okay. Similarly, if p equal to 2, there is nothing. I mean, this 2 by 2 is similarly, if p equal to 2, then also mod t, that exactly means mod t is K of H. This is what we want. Okay. So now t is equal to u times mod t, polar decomposition. Okay. We know that compact operators form an ideal. Okay, it's an ideal. So if mod t is compact, then t is compact. Okay. So this is what we want. Okay. So we proved that if it satisfies this condition 1 or 2, then it's a compact operator. So if you want to see anything, if you want any clarification, you ask me. Okay, I have written everything clearly. I hope there is no mistake. Even if there is some mistake, you find it out. Okay. Okay, so this is what we want to define. So any positive operator. So here we have dealt with positive operators. So here we have make the definition, following definition. Okay. So B1H, this is what is called trace class operators. Equal to, so for the time being, I edit like the span of T in B of H T greater than or equal to 0 and trace T is less than infinity. Okay. So we take all those operators which trace is less than infinity and take the linear combination of that, complex linear combination of that span of this. See, it is like this. If you want to talk about L1 function, how will you define an L1 function? You integrate the mod of that, and that should be less than infinity, right? Then you define all those integrable operators as integral of mod of less than or equal to infinity. I mean, all you talk about all, and I say a function is integrable if integral mod of is less than infinity. Here, instead of that integration, this trace is the non-commutative analog of integration. It is just the non-commutative analog of integration, basically. It's like it's a linear functional, and it is like, I mean, it's a, I mean, integration satisfies all these properties, right? It's a linear functional on all those things, and we will prove that. We will prove this is equal to all those t in B of H. Trace of mod t is less than infinity. I mean, I'm defining all trace class operators as span of all positive operators with trace t less than infinity. Finite linear combination of, okay, finite linear combination of positive operators whose trace is less than infinity. I'm saying which is also same as all those t, all those t whose trace of mod t is less than infinity. Okay, so these two are same. That's what I want to do. So I am taking this as the definition and will prove that this is equal to this. Okay, this is not the definition. This is equal to this. Then you can take this as the definition and then prove that. You can see that this coincides with the, this is similar to the definition of integrable functions. You take any function and you can, any f can be written as f1 plus if2. If you have a complex function, then you can write any real valued function as f plus minus f minus. Okay. So here also all those things are true, but we are not going through that. See, to write any operator as a difference of any operator can be written as linear combination of two self-adjoint operator. T1 plus IT2, you can write it. But then you have to do something more to write any self-adjoint operator as T plus minus T minus, where T plus and T minus are positive operators. You have to do, you need to know spectral theorem or something. You need to use functional calculus. You can do something else also. For example, this I say, this is, I'm not going to use it. See, if you have any self-adjoint operator, see self-adjoint, that is T equal to T star. Okay. See, I don't know whether it is defined earlier. If you have two self-adjoint operators, this is, okay, I'll come back to this whenever I need. I don't want to do this. I want to write that any self-adjoint operator can be written as, you can write it like this. For example, informally I say this, if I need it, we will use it later. T can be written as norm T plus T minus norm T minus T. So 1 by 2 you have to use. So you can write it like this. This will be a positive operator. This will be a positive operator. This is one way of writing. The other way is to use something called functional calculus, which we haven't done. Okay. Okay. So now we want to prove this, the following. So towards that, I prove the following proposition. And for the time being, I'm taking trace class operators as linear span of all positive operators whose trace is less than infinity. Okay. So then you can extend the definition of trace. So we can extend the definition of trace as a linear functional. As a linear functional on this, we will indeed prove that B1H is a Banach space with respect to the trace norm, not with respect to the operator norm. With respect to the trace norm, this will be a Banach space. Okay, so we can extend trace as a linear functional to B1H because it's just linear combination. You can take the complex number out and you can write it, and it will follow that. Since all this inner product, everything is in, it will follow that. It will look like TEN. Okay, you can write it like this, which is also equal to this. Okay. So we want to prove the following proposition. Okay. So what is the proposition? I want to prove this equality. Okay. So before that, I want to prove that B1H is an ideal. Is a two-sided star ideal. Okay. So that's what I want to prove. And B1H equal to all those T in B of H. It's the trace of mod T is as an. This is equal to that. Once we prove that, it will be clear. For the second statement, I just want to use polar decomposition. So this is what we did for compact operators here also. Mod T is compact, imply T is compact. So here also mod T is trace class. I want to prove T is trace class. So once I prove the ideal property, it will be clear. Okay, so that is why I want to prove the ideal property. So I want to prove the ideal property. So here I am taking B1H as linear span of positive trace class operator. Okay. Okay. So how do we do that? For this, I need a so this I may use later, so I will write it here. So this is what is called polarization identity. I think you know 4 times inner product xy equal to summation I k equal to 0 to 3 I power k x plus I power k y x plus I power k y. I think you must have verified this. Okay, this is just you are using the linearity of the first variable in the inner product and the anti-linearity of the second variable in the inner product. You do that and you will get it. And I haven't verified it recently. I have been giving this as exercise, and this is a well-known thing. I have not gone through the verification recently. Recently means last 20 years. I have been giving it as an exercise. So you can do this. Okay. So similarly, so it is just the same proof is imitated here. Okay. Oh, no. Similarly, this one. Similarly, for T and S in B of H, this is 4 times T star S. I should be careful. So the first variable here is conjugate linear. The second variable is linear. So it will look like this. K equal to 0 to 3 I power K S plus I power K T. There is no inner product. Star S plus I power K T. Okay. So you verify this. This is what is called polarization identity for operators. There is nothing, there is no difference between the earlier polarization identity and this. It's just the proof. The point is, this is also an inner product kind of thing. This is an inner product taking values in operators. See, if you do, I mean, not to use some fancy word, but if you could have heard about modules, Hilbert modules or something. So they are spaces with inner product, and the inner product takes values in operators. I mean, some C-star algebra or Banach algebra or B of H or something, B of H. So this is like an inner product, operator valued inner product. Okay, T star is it will satisfy all the property of inner product. So if you take it is I mean, actually here it is anti-linear. You can take TS star, but this is also okay. This is anti-linear the first variable, linear the second variable, and that is why I have written it in a different way. I have written the star here first, and that is one thing. Another thing is T. If you take T equal to S equal to T, then it becomes T star T, and T star T equal to 0, it will imply T equal to 0. So that is also satisfied. So this is like an inner product. So it basically the idea from inner product, you can prove it. Okay. So this is an exercise. The same verification will go through here. Okay. Okay. So I want to use this polarization identity. So how do I want to use? So this I want to what? So what do you want to prove? I want to prove that B1H is a two-sided ideal. First, the star ideal is clear. Okay. So B1H, what is B1H? B1H is some linear combination of T. I mean, T is in B1H. That means T is a linear combination of positive trace class operators. And if you take star of that, positive linear operator will become positive, stay as it is. Only the linear combination will become lambda 1 become lambda 1 bar, lambda I become lambda I bar. And that is again linear combination of positive things. So this implies it's clear. Okay. From the definition, T star is also in B1H. This is clear. Okay. So we only have to prove the ideal property, two-sided ideal property. So if T, so, and it is enough to prove, I mean, we want to prove the ideal properties enough to prove the following. S is in B of H, and T is greater than or equal to 0, because we are going to deal with the linear combination of positive operators. So it's enough to prove for one positive trace class operators with trace T is less than infinity. So we want to prove that. ST is in B1H. Okay, that's what we want to prove. Okay, ST in B1H, whatever that means. Okay, ST is linear combination of positive trace class operators. That's what you want to prove for any S in B of H. Okay, ST or TH, that doesn't matter. I mean, if you prove TH, that's I mean, if you take by taking star, you can prove ST is also there. Okay, so we want to prove TS is in BFH. Okay, so how do we prove TH is in BFH? So T is positive operator. So TS is equal to T power half T power half S, and I want to use this polarization identity. Okay, so this is equal to, I keep it like this. Okay, this is my T. This T power half is T. That T power half is S, which I want to use it here. Okay, so that will imply this is equal to, I will get a star here. So 1 by 4 into k equal to 0 to 3 I power k, and here, so S plus T. Okay, so, and I should take the star here. So S star, and there will be a T power half here. S star T power half plus I times k T power half. Okay, not a star. T power half S plus T power half I power k star, then the same thing, T power half. And this is equal to, okay, I can take this T power half outside. I mean, this, if you take the star, it will become S star T power half, and this T power half will remain as T power half because they are self-adjoint. And you can take the T power half will come in the left side, and you can take it out. So this you can write it as I power k I identity. And here the T power half is in the right. So that is in the right side. Here it is in the left side. I am always confused with right and left. So you will get this. Okay, T, then you will get S plus, here there is a star, and here I power k T. So this is what I get. Okay. So let us write it as summation k equal to 0 to 3 I power k, some Vk star T Vk. So Vk are some operators. Okay. Now the claim is the following. If I prove this claim, then this is, say I want to prove that this TS is trace class. Okay, I have written TS as some linear combination of operators of this form. So we have Vk star T Vk. So the claim is the following: if T greater than or equal to 0, trace T is less than infinity, and some A is an operator in V of H, okay, then A star T A is in B1H. That is also trace class. Okay, this is the claim. So once I prove this claim, it's maybe I use B itself by A. V star TV is also trace class. Okay. So once I prove this claim, it's clear because then it is sum of trace class operators. So that is trace class. Notice that if T is positive, then V star TV is also positive. Okay. In fact, V star TV XX, if you take, that is equal to T VX VX. Okay. That is positive. Okay. Positive means TXX greater than or equal to 0, and this implies this is positive. Okay. So if you have any positive operators, then you can take some other operator and write it as S V star TV, then that's also positive. So this is a positive operator. Okay. So we can talk about trace of V star TV. It may be infinity, but still we can talk about this. Okay, trace star V. Now this is equal to T is positive. Now I want to bring in this V. So that will become VN. That doesn't give anything. I can bring here T power half And write it as V star T power half T power half. Okay, V. Now I'm using this property. Trace of S star equal to trace of S star S, which we have proved. Okay, using this. Using this, I get this is equal to this is one thing and this is one thing. Okay, T power half V star T power half. Okay. Now that is equal to summation n equal to 1 to infinity for some orthonormal basis. T power half I'm swallowing one step. Hope it's all right. Okay, I will explain. V star T power half En, then T power half will go. So V star T power half En. I mean, trace means whatever I have here inside the trace, En. Then I am taking this T power half and V as on the other side as star. Okay, that's what I have done. I hope this is okay. Okay, this is equal to this. Okay. No, I don't need to do that. I don't need to do that. I can only take T power half that side and keep V here. V star. Okay. Now V star is a positive operator. Okay. I mean, for any positive operator, positive A, let's say, for any positive operator, A, okay, AXX is less than or equal to norm A times norm X square. Norm X is nothing but XX. Correct? Okay, you can write it like this. So because of that, this thing will become, you can take the norm VV star outside and summation n equal to 1 to infinity T power half En and T power half En, which I can take it as, here it is less than or equal to, sorry, V star summation n equal to 1 to infinity T En, which is equal to norm VV square trace of T. Okay, so this is less than 50. So we have started with trace of that. So this implies V star TV is in V1H. Hence the claim. And we only had to prove the claim. Okay. We had a claim, and using that claim, we prove that yes, TS is a trace class operator, and from that everything follows. So all these things imply that what we have proved is B1H is two-sided ideal. Two-sided star ideal. So that's what you have to. Any doubt you can ask me, and you can also tell me if you something is not visible in the screen. Okay. Because I'm writing big and maybe I should write smaller. Because the screen is in this setup, it's coming and you asked for it. So it's a two-sided ideal. Okay. So now if mod T is in B1H, okay, then U equal to, sorry, T equal to U mod T, okay, polar decomposition. Okay. Okay. So since it's an ideal, this implies T is also in B1H. Conversely, if T is in B1H, okay, then notice that mod T is nothing but U star T. See, U B equal to T equal to U mod T. Now U star T equal to U star U mod T. But U star U is identity in the polar decomposition. The polar decomposition is unique with respect to polar decomposition is what? Any operator T can be written as U, which is a partial isometry, T a positive operator. And it is indeed the positive square root. With the property that the kernel of the positive operator and the kernel of the partial isometry and the kernel of the original operator, everything coincides. So with respect to that condition, the polar decomposition is unique. So if you go through the proof, that is the proof. And in the polar decomposition, the partial isometry means what? It is you can partition the Hilbert space into two orthogonal subspaces, one orthogonal to each, and in one of them it is actually an isometry. So that's what a partial isometry is. Okay, so this U star U is an isometry on the range of mod T. If you go through the proof of that, that is the case. So it is, this is one of the implication of polar decomposition. Polar decomposition says this: T equal to U mod T, and it follows from the polar decomposition that U star T is equal to mod T. Okay, where mod T is, mod T is T star T power half. Okay. Okay, so because of this, mod T is in B1H. Okay, so we have proved the following. B1H is nothing but all those operators such that trace of mod T is less than infinity. Is it fine? Any question? Okay, so I have some more time. So this is about trace class operators. We will do more about trace class operators. We will come to that. Before that, I want to define what is called Hilbert Schmidt operator. So B2H. These are what are called Hilbert Schmidt operator. The space is called Hilbert Schmidt operator. Hilbert Schmidt. Hilbert Schmidt operators. Is all those T in B of H such that trace of T star T is less than infinity. Trace of T star T is less than infinity. Notice trace of T star T is equal to summation T star T En. So this is equal to summation Ten, which is just norm Ten square. Okay. So sometime people start with this, define the Hilbert Schmidt like this. You define a Hilbert Schmidt operator such that which is defined as this summation of norm Tn, this n equal to 1 to infinity. As this, then prove that this sum does not depend on orthogonal basis, then come to trace class operators. I don't like that. I want to define trace first and then prove this. Okay. So this is trace class operator, and for trace class operator, this is nothing but this. So you can define norm T2, okay, to be trace of T star T power half. Okay, you can define it to be like this. Anyway, let's come to that later, because I want to prove that this B2H is actually a Hilbert space with respect to this T2. Okay? We will come to that. Before that, we do the following proposition. So what is that we want to prove? B2H. B2H. What is B2H? Is a star ideal. Star two-sided ideal. And we have already proved both B1H and B2H as contained in, they are all compact operators. We have already proved that. Okay. So we want to prove this. And star ideal. So first star is clear. T is in B2H. Then trace of T star T. We have already first thing we proved is trace of T star T equal to T star. So this implies T star is in B2H. Okay. So this is star is clear. Star ideal is clear. We have to prove it's a, and that is also clear. If T is in B2H, then S in B of H, then trace of ST star ST equal to maybe TS star, whichever, doesn't matter. Maybe it just doesn't matter, whichever. Okay, this is okay. I mean, because star is there, we can prove the other inequality. So here TS star TS equal to trace of S star T star TS. Okay. So now this trace is finite because T is trace class. So trace of T star, I mean T star, trace of T star T, since T star T is in B1H. Okay. You can multiply T star T on the left hand side by S star and right hand side by S because it's an ideal. So this implies S star T star T, S is also in B1H. And that is what it means by that. So this implies TS is in B2H. Okay. And by taking star, it's clear ST. I mean, you will get S star T star, then it doesn't matter. Okay. So we proved that it's a two-sided ideal. So Hilbert Schmidt operators, they form a two-sided ideal. If you have any questions, you stop me, or if you want me to go through something again, I can go through. Okay. Because I don't see your faces. I don't know whether it is clear or not. Okay. So now we want to prove the following proposition. B2H. So is there anything else? So I have to prove the second one. Okay. So let us see the following. I mean, more or less we have proved everything. I'm just collecting all those things. Finite rank operators are contained in trace class operators. B1H is contained in B2H, is contained in K of H, is contained, of course, everything is in B of H. Okay. So this is very similar to, of course, finite rank operators in finitely many coordinates. B1H is like L1, similar to L1 is contained in L2, small L1 is contained in L2, is contained in C0, is contained in L infinity. But these are all non-commutative. See, if you fix an orthonormal basis, if you take all diagonal operators with respect to the orthonormal basis, okay, that is like L infinity. All bounded operators, all diagonal operators with respect to an orthonormal basis, that is just L infinity. But then you can change the orthonormal basis. You can take different orthonormal basis. So they give all operators, right? All diagonal operators. Of course, B of H need not contain all diagonal operators. They have something else. They have something more. So, I mean, for even normal operators in B of H will not be diagonalizable. But suppose, so that is like, so that is like L infinity. Compact operators, they are diagonalizable. And if you fix an orthonormal basis, all compact normal operator with respect to that orthonormal basis, diagonal compact operator with respect to that orthonormal basis is just a C0. Okay, any sequence converging to 0 will give an operator. Okay, but then you can change the orthonormal basis, and not just that they are only normal operators. You can take by using some polar decomposition, you can get different operators. You can take two different orthonormal bases defined from one to other, and you get lot of compact operators. So, but compact operators are non-commutative analog of sequences converging to 0. So this Hilbert Schmidt operators are non-commutative analog of small L2, and trace class operators are non-commutative analog of L1. Okay, finite rank operators are just finitely many coordinates, just functions on finite set. Okay, it's a non-commutative analog of functions of finite set. So the same inclusion holds here. So that's what I want to say. So first thing is clear, proof. So if T is a finite rank operator, Okay. Then mod T is also a finite rank operator. Okay. So mod T is finite rank means it's a compact operator if you want. So there exists E1 up to En and lambda 1 up to lambda n and TEI equal to lambda EI and T is 0. I mean, and E1 up to En per is contained in kernel of T. Okay, that is how it will look. Okay, because it's finitely many, because it's a normal operator, mod T is a normal operator, it will have it is diagonalizable, and it cannot have infinitely many, I mean, orthogonal elements where it is non-zero. Okay, so it will be concentrated on only a finitely many of them. So because of that, it will look like this. So this implies. So then this implies, then it's of course summable. So this implies this is in B1H. Okay, so that is clear. So any finite rank operators are trace class operators. So now the next thing, suppose T is a trace class operator. Okay, so that just means mod T, trace of mod T is less than infinity. Is less than infinity, right? Okay. So. Now we want to prove that T star T is also T star T is trace class. I mean, I want to prove this containment. Okay. B1H is contained in B2H. So I'm taking a trace class operator. I want to prove it's also a Hilbert Schmidt operator. So I have taken a trace class operator. That means trace of mod T is less than infinity. Okay. Now I want to talk about trace T star T. T star T is mod T square, right? But then I want to write it in this form. I mean, T power half mod T power half. I should have proved a bit. Anyway, let's now trace of T star T. I mean, we can make sense of it. It may be infinity. We have to prove it's less than infinity. Because this is positive, we can always make sense of this. That is equal to summation En. And for some orthogonal basis. Now that is equal to, as I have written, mod T power half En. Maybe I should have it inside T power half En, T power half En. This is okay. Summation n equal to infinity. Now this is equal to, so this mod T you can take it out. Norm of mod T. Norm of mod T same as norm of T. Okay, C-star identity will tell you. So I can write it as this is less than or equal to norm of T times summation n equal to infinity T power half En, T power half En. Now that is equal to T mod T. So, oh, sorry, this is mod. I'm making mistake. You are not telling anything. Okay, mod T. Now this is equal to norm T times trace of mod T. Now this is less than 50. So this implies, I mean, we have assumed T is trace class and we have proved that T is in B2H. Okay. So we have proved first inclusion, second inclusion, and we have already proved everything is compact operator, everything. So we have proved the proposition. Okay. Okay. So more time. Proposition is a Hilbert space. With respect to the following inner product, which is called Hilbert Schmidt inner product and operators, equal to T star S. Okay. Because we want it antilinear in the second variable, linear in the, I mean, this is a problem with mathematicians. So physicists For physicists, the inner product is linear in the second variable, anti-linear in the first variable. That is the right thing to use, of course, actually. But we are using, mathematicians are somehow using this. So this is the inner product. This is an inner product. So this is clearly linear in the first variable, anti-linear in the second variable, conjugate linear in the second variable. And what else? What is if you, oh, sorry, I missed trace. You are not saying, I mean, we have inner product takes values in complex numbers. Okay, so I need trace. I forgot trace. This is not an operator value inner product. This is a genuine inner product. Okay, on B2H. So I have to take trace. So when you take trace, it becomes a complex number. Okay, so inner product between S and T is defined as trace of T star S. So first we have to prove that this is well defined. Oh, I forgot one thing. Wait. Sorry, I forgot something here. Well, I haven't, I said B2H is a two-sided ideal, but I haven't verified that it's actually a vector space. Okay. So this is what I have to verify. Also, so to verify vector space, if, I mean, scalar multiplication is okay. That is clear. You just have to, you can take the scalar out of trace. So it's okay. But we have to prove that if T is in B2H, in the trace is linear. So if you have T1, T2 are linear, then trace of T1, T2, T1 plus T2 is also finite. But here it's not linear. Okay, the Hilbert Schmidt definition is not linear definition. So we have to verify that if T and S are Hilbert Schmidt, then we have to verify that T plus S is also Hilbert Schmidt. Okay. So to verify that T and this are Hilbert Schmidt means T star T trace of this is finite, and S star S trace of this is finite. That's what we have. Now we have to verify something about T plus S star, T plus S. You have to verify this. You have to connect these two things. So for that, I do the following. Okay. For if T and S are in B2H, then T plus S star, T plus S, okay. T plus T minus S star, T minus S equal to, I mean, this is just it's just non-commutative manipulation, the star, okay, A plus B into A minus B kind of thing, except that you have a star here, so you have to, this is equal to 2 times T star T plus S star S, right? So you can easily verify this. So this implies T plus S star, T plus S is less than or equal to, as operators, I will explain what it means, T star T plus S star S, meaning, I don't know whether Shruti said this. See, if two operators, A and B, are self-adjoint operators, okay, then we say A is less than or equal to B if B minus A is a positive operator. Okay, that's what it means by, I mean, we have to say A is less than or equal to B for some, I mean, for any two real numbers, we can compare. Similarly, you cannot compare any two self-adjoint operators, but if this is true, then it's comparable. Okay, B minus A is greater than or equal to 0. What does it mean? This just means that is B minus A XX is greater than or equal to. This is the definition of positive operators for all X in H. That is AXX is less than or equal to BXX. So this is the definition of this. Okay. So this just says that if the difference of two self-adjoint operators is positive, that's what it means. B minus A is positive means difference of two self-adjoint operators is positive. that means that one is greater than the other. So here, this whatever we have here, the left hand, the right hand side, minus this t plus s, this right hand side, that difference is whatever we have in the second term. Okay, so it is positive. Okay, so t plus, that's what it means. So that's what I have concluded there. Okay, so this will, so when you have two positive two self-adjoint operators, one is less than the other, then you can take the inner product with x and x, and that will be less than 2. That's what it means. Then you can take the trace over some orthonormal basis, then that will also be less than or equal to. So this implies trace of t plus s star t plus s is less than or equal to two times trace of t star t plus trace of s star s. Okay, so this is less than 50. So this implies we have to do all this to prove this B2H. Okay, so B2H is a vector space. Okay, so we have proved B2H is a vector space. So when I said ideal, ideal is also a vector space in the algebra. Okay, an ideal in the algebra is a vector space which satisfies the ideal property. Okay. I have 15 minutes. So now I want to prove that B2H is Hilbert space. Okay. So this is a Hilbert, this is a, yeah, so this is linear in the first variable. Okay, if you put a lambda here before here, then that lambda will come here and you can take it out of the trace, because trace is just sum of inner products and inner products are linear. So you can take it out. Similarly, if you put a lambda with t, then that will come with this t star here. So it will come as lambda bar, which you can take it out as lambda bar. So it's anti-linear in the second variable. Okay, those things are clear. And we have to only verify the positivity property. So to verify that, we know this. So if inner product TT, this Hilbert Schmidt operator, I may write this Hilbert Schmidt or I may not write. Okay, inner product TT is equal to trace of T star T, and we have already proved trace of positive operator is greater than the norm of T star T, okay, which is equal to norm T square, C star identity. So this implies if this is equal to 0, if TT equals 0, implies T equal to 0, because norm T will be equal to 0. So we have Hilbert Schmidt operator. So this in particular, which says that we have this, and we defined this. Okay. Which is equal to trace of star T power. So whatever the inequality says that norm T2 is greater than or equal to norm T. Okay. So we have to prove that it is Hilbert space. We have to prove that it is complete. So that is the only thing we have to prove. So suppose Tn is Cauchy. It is Cauchy in the Hilbert Schmidt norm, the norm we have defined. We have proved that it's an inner product, so it gives rise to a norm, and we have to prove that it is actually complete. It's a Hilbert space. So suppose Tn is a sequence of operator is Cauchy in the Hilbert Schmidt norm. Okay. Then we know that Hilbert Schmidt norm is greater than the operator norm, and operators are complete with respect to then Tn minus Tm. 2 is greater than or equal to Tn minus Tm, this norm. So Tn is Cauchy in operator norm. Okay. There exists a T, but then remember that Tn's are compact operators. Tn's are in K of H. So T is also in K of H, because K of H is the closure of finite rank operators. In particular, K of H is closed. Okay, so there exists a T in K of H. such that Tn converges to T in operator now. Okay. So we have got a limit in operator now. We have to prove that it actually converges. The limit, I mean, whatever we got as a limit actually converges in Hilbert Schmidt now. So we want to prove, that is what we want to prove. We want to prove it is complete with respect to Hilbert Schmidt now. So we want to prove Tn converges to T in the Hilbert Schmidt now, which we have defined. Okay. We have convergence in operator now. We have to prove that it converges in Hilbert Schmidt now. Okay. How do you prove it? Yeah.
These topologies are stronger than the norm topology.
Yes, that's what this says, no? Hilbert Schmidt norm is bigger than operator norm. If something converges in Hilbert Schmidt norm, then it converges in operator. Right? That's what this says, right? By definition, Hilbert Schmidt norm is greater than the operator. So it is stronger topology. Stronger means the convergence in the stronger topology should imply the convergence in this weaker topology. So now this is stronger than, I mean, that is why closed sets are, see, if you take the completion of, if you close the Hilbert Schmidt operator in norm topology, you should get B of H, compact operators. Because if you take the closure of finite rank operators, you get compact operators. Finite rank operators are contained in Hilbert Schmidt operators. Okay, so if you close Hilbert Schmidt operators with respect to norm topology, then you will get all compact operators. But then here I am saying, if you have a stronger topology, then the closure is smaller. Okay, if you close with respect to a weaker topology, you will get a bigger set. Okay, just think about it. Okay.
Yeah.
So why did 2 vanish? Okay, so we want to prove this convergence, Tn converges to T. What happened? 2. I wrote 2, it gets vanishing. So Tn goes to T in the Hilbert Schmidt operators. So that is what we want to prove. So we want to prove something like that. So for that, we cannot dominate the Hilbert Schmidt norm by operator norm, but we can do something. We can use finite rank operators to do that. Okay, so suppose. So we know that T is compact, Tn is compact, everything is compact operator. So they are limit of finite rank operators. So if you prove that, if you prove whatever I'm going to do. So let me write it. Suppose P is finite rank projection. Finite rank projection. Okay, then I hit this. So I want to take the Hilbert Schmidt norm. So anyway, I want to take square because these are an inner product thing. I have to take square P into Tn minus T, and this is indeed equal to trace of T star. P square is P, so P Tn minus T. Okay, right? So P is a finite rank projection. This is equal to that. I have just written the definition. Okay. Now this is also equal to, I can write it like this anyway. P of Tn minus T star, Tn minus T, P. Okay. See, now you see that Tn converges to T. I mean, let's take some m. Tm converges to T as m goes to infinity in now. Okay. So this will imply that Tm, I mean, that is Tm minus T goes to 0. So in particular, Tm minus T xx. Or if you, I mean, it's also true that you can take I mean, norm is continuous if you take star, if you take product, jointly continuous, and if you take products. So norm topology is a nice topology. Okay. So because of that, Tm minus so this implies Tn minus Tm star Tn minus Tm goes to 0 as m goes to infinity, right? I'm fixing n. Okay, this is clear. Okay. Now, if you have some operator, sequence of operator going to 0, then that Snxx is also going to 0. I mean, whatever I have here, that operator I put it here and xx will goes to 0. Okay. But then in this trace, there are only finitely, see, you can take only finitely many of those terms remain. See, this P is a finite rank projection. You are hitting this Tn minus Tm by P, a finite rank projection. And that will have this kind of inner product, something Txx. Only finitely many terms will be there. So this implies that is equal to, this is equal to limit m going to infinity, trace of P Tn minus Tm star Tn minus Tm P. See, this is because P is a finite rank projection. And if you evaluate this trace, you can evaluate using orthonormal basis for the range of P, and then by union orthonormal basis for the range of P per. Okay. So the range of P per, the operators, I mean, they are all 0 here. Okay, because you are hitting it by P on both sides. So only those orthonormal things which are inside the range of P will remain. And the sum is a finite sum. So you can take this limit. Otherwise, you cannot do it. Okay. I mean, Tm converges to T in norm does not mean you can take the limit inside the trace, because the trace is a summation over, unless there is some uniformity, you can't take the limit inside the trace, because the trace is a sum over infinite, it's an infinite sum. But here the sum is over only finitely many, because P is a finite rank operators. Okay. I don't want to write each and every step. So if you think about it, it will be clear. Okay, since P is finite rank. Since P is finite rank. Anyway, if you don't get it, you tell me. We will discuss this. We will have one class for discussion. You go through all these things. If you don't understand, you tell me. Okay. So because of finite rank, this is true. Okay. Okay. So now we have got all these things. Now, what is it? Limit m going to infinity. Now this is less than or equal to lim sup of trace see each and every that limit whatever we have for each n, that is less than or equal to this, right? Is it right? Lim sup over what? Lim sup over m, right? Is okay? Yeah, I have P here and I have just removed the P with lim sup. This limit may not exist, so I'm just writing it as lim sup. Lim sup of course exists. Okay. And these are all positive numbers, not complex numbers. Okay. We can write it like this. And there is no P here. And this is true for all P. So what we have is the following. For any finite rank projection, this whatever I have in the left hand side, this is less than or equal to lim sup of this. Okay. They are all positive numbers. So this implies norm Tn minus T. This is true for all finite rank operators. Okay. 2. See this now. What is norm T and T? This is just summation like this. Summation of trace of Tn minus T star You don't see, this is just the summation of norm of Tn minus T En square, right? So if you put a P here, the summation is over just some En, right? If you have a P here, then the sum is just finite sum. So for each such finite sum, this is less than or equal to this. So this is also less than or equal to this. That's what I'm saying. Whatever this Hilbert Schmidt norm I have written, this is an infinite summation. But by hitting a finite rank projection, I say that for all finite rank projection, this is less than or equal to some number. Okay, for all finite rank projection, then the infinite sum is also less than or equal to that finite sum. Okay, that's what I'm saying. So this implies this is less than or equal to this lim sup of this m trace. So, but this is just norm of Tn minus T. Square, right? But this goes to 0, so this should also go to 0. This implies T goes to a very standard technique. Is clear? See this Tn minus T, if you want to take the Hilbert Schmidt norm, which is just trace of the Tn minus T star Tn minus T summed over En, an orthonormal basis, which is an infinite sum. But I'm hitting with a finite rank projection. So you can take a finite projection. Okay. So all those finite sum, all finite sum is less than some number. So the infinite sum is also less than that number. And these are all positive. Okay. We are dealing with positive sum. Okay. So because of this, Tn minus T, Tn goes to T in the Hilbert Schmidt. Hope it's fine. Anyway, go through it. If you have any doubt, you ask me. Okay? But this is an important proof. You should go through. If you have any question, you ask me now. Otherwise, I will end the meeting. Okay, I end the meeting. If you have any question, you ask me in the next class.